We'll start lecture on uncertainty in GIS and error propagation. In the previous lecture, if you remember, in data quality, we have seen few things. Few things means different stages where errors can be introduced in data. And since error can be introduced in data because of those things, so we have to take care about quality of data, like accuracy of the data, then completeness of the data creation process, lineage, logical consistency. Those things we have to see to check that is the data qualified for our application or not. But today we'll see a little ahead about errors in GIS data as well as its propagation, how it is propagated and why it propagates. So as we know, GIS is the real world representation. In GIS database is basically real world representation or computer representation. So one important thing, always error does not mean it is introduced by mistake. There can be situations where error is introduced in database because of natural limitation, technological limitations, like we have seen in previous lecture, vagueness and ambiguity, where we are not sure where boundary of one feature is stopping and where boundary of another feature is starting because of randomness in natural phenomena and non-crisp boundaries of availability and natural phenomena. Also, when the imaging is done at the boundary, there will be mixed pixel. Mixed pixel means pixel having signature of more than one features. So if pixels are having uh, value or signature mixed from multiple signatures, so it is difficult to identify how to assign that pixel to some class. So because of these things, errors are introduced. And sometimes we have to be uh, take precaution to avoid the error, and sometimes even it is okay to have some error. It depends on the application. Like in previous lecture, we discussed about the application. If you have to work on small scale land cover analysis, it's okay to have some error of 10 meters, 20 meters. But when you have to work on very large scale application like navigation, so in that case, error may lead to accidents also. Different roads is not marked properly, junction is not marked properly, so it becomes uneasy even when you are driving, and it becomes uneasy when you are searching for or going for some location. So these uh, steps we have seen previously and discussed. Uncertainty in GIS database could be of it could be introduced at these three stages due to conception, ambiguity, and vagueness concept. Then measurement and representation, how we are representing the feature, we are representing in the form of point or polygon or line, and how it should be represented exactly. That is sometimes debatable topic. Someone will say that I want to represent road in the form of line, and someone will say since road have some width also, it cannot be line always, it can be polygon. Then at which scale you should start representing line in the form of polygon or in the form of line? Sorry, at which critical scale above which you should represent road as polygon or road as line. So that is not very, that cannot be defined very well. So there will be confusion. And yes, suppose because of this confusion, suppose road was to be represented in the form of polygon, but you have represented in the form of line, and line does not have any width. So the uh, neighboring polygons will have attribute error for that particular location. And in analysis stage also, error can be introduced due to numerical representation. Simple, yeah, these things we have seen, and we will see even in more detail. In analysis stage, error can be because of approximation in the model, because as you know, the natural phenomena are not as easy to model in the form of linear equation. All the natural phenomena, obviously force equal to mass into acceleration, that is very simple phenomena, but many natural processes are not uh, easy to model in the form of mathematical equation or linear mathematical equations. For example, climate change. It is not possible to model climate change very easily in the form of linear equations. And you cannot be sure that what are the parameters, factors responsible for the climate change. It is temperature or in land use pattern, it is pollution or what, and what is the collective relationship of these factors for climate change, not possible to model easily. So what we do, many times you may have seen across the literature, linear model is fitted, simple linear regression, multiple linear regression, exponential, polynomial function is fitted. These are some standard functions which are generally fitted. Or sometimes you may see Taylor series approximation is used, logarithmic functions are fitted. But do we know these functions should be there and they are exact? No, everything is approximated. Approximately overall, they may fit, but not exactly. So because of this approximation, there will be some error in the output. Approximation can be in the form of estimation of model parameters. We'll see in detail about model parameters. Then next comes numerical error in the computer. For example, simple, suppose you have to represent a coordinate in the form of longitude and latitude. Let's say its latitude is 20.495 degrees. Let's say this coordinate needs to be represented in the computer, but because of some limitation, your computer is able to store only 3 digits after decimal. So computer is storing this coordinate as 20.495, and this 6 is not stored in the computer. And with this you can see the 6 is at fourth place of decimal, which is 0.0006 degrees. It seems very less number, but when you convert this 0.006 to meters, let's see what you will get. 0.006. If you convert this number, which was the difference between actual and the represented value, So if you convert it, considering 1 degree equal to 100 kilometers, so if you multiply 0.0006 with 100, uh, 100 kilometers, you will see that this is equal to 60 meters. So 60 meters is a big number when you are talking about large scale application. But when you talk about small scale application, 60 meters will not be much. So you can see because of this fourth place of decimal, 60 meters of error is introduced in your database. This is just one example of how numerical error in computer can lead to larger errors in the form of position as well as attribute. So these four points which are never met, error may we may ignore error. We may be ignoring error because of these assumptions that digitization is error free. It cannot be error free even it is manual digitization or automatic digitization. If it is automatic digitization, there will be different kind of errors. If it is manual digitization, there will be error in placing the boundary in case of automatic identification of boundary. Another error source of error is data source is error free. There is an assumption that data source is error free. That is also not true, cannot be true. So when we start digitizing or start creating vector data, we assume that whatever we are doing that is perfect. We are able to digitize 100% accurately. That one assumption we keep in mind. Another assumption we keep in mind that data source whichever we are having, either take any XYZ satellite, Landsat, Sentinel, list, whatever you take, anyway, list is sensor, not satellite. So you take any data and it is not error free. There can be error because of mixed pixel, there can be uncertainty because of atmosphere, point spread function of the sensor, radiometric issues may be there. So these issues collectively affect our ability to identify the feature. And if our ability to identify the feature is affected, we will not be able to identify it properly. And if we are not able to identify it properly, it will lead to error, either in position or in attribute or in both. And once our data is having error, it will lead to further errors in analysis. Because when we have created the data, it is not that we have created data, we are very happy with this data. It's not like that. We have created the data for some purpose, to solve some problem, to rectify some issues. So, and if this has to be done, means if some problem has to be solved, some analysis has to be done, which means some tools need to be used, some algorithms need to be used. If this is the case, then error will increase because the nature of error is additive in general. Additive means error in stage 1 will get error from the model used, and in output you will have more error. And if another analysis is done over the output, more error will be uh, introduced in the last stage. There may be some exceptions where after a model error have reduced, but generally error is additive in nature until there is some precaution taken to reduce the error. Another assumption is that boundaries are sharply defined. No, boundaries are never sharply defined in case of nature, and even if it is sharply defined, it becomes difficult to identify. For example, you are digitizing object kind of phenomena, and as you know, object kind of phenomena are always discrete. To consider you are digitizing the buildings, footprint of building or rooftop of the buildings. So building boundary is sharply defined, that is true. But uh, when you will try to identify the building boundary from the satellite image because of orthographic effect, because of look angle of camera, shadow, because of these factors, exactly identification of boundary will or may not be possible always. Sometimes it may be possible. So let's modify the sentence. Uh, Boundaries are not sharply defined in case of natural phenomena, but in case of man-made phenomena, boundaries are well defined, but because of different factors, look angle, shadow, uh, atmosphere, mixed pixel, identification will not be very much proper. Algorithms are fully deterministic, so that is also a false assumption. Algorithms are never fully deterministic, or mostly they are not fully deterministic until there are some fundamental characteristic equation like F equal to ma. Until there is some such kind of equation, the rest of the equations processes cannot be captured, may not be captured fully in the form of equations. There will be certain level of approximation. Now, error can be in the form of attribute or in the form of position. Apart from the data quality issues, other data quality issues like uh, completeness or logical consistency, those kind of quality parameters are different. Here, if you talk about purely error, it can be either attribute or uncertainty. Position. So, what is attribute? Attribute is defined as the characteristic uh, property or inherent property of spatial data. Here, in case if we talk about spatial data, or in general, attribute is the characteristic property of some data. In case of spatial data, it is characteristic property of spatial data. For example, ownership of the land, that is a characteristic property or inherent property, you can say. Name of land use class, that is also attribute. Population of a city, that is attribute. Area of a city, that is attribute. So as we know, real world can be represented either in the form of field or in the form of object, depend on the kind of phenomenon. Accordingly, attribute data is also classified in qualitative and quantitative manner. Uh, if uh, Qualitative manner means the attribute classes are given names. It can be ranking or names. But in case of quantitative measurements, exact numbers are defined. So for qualitative category of attributes, it can be ordinal or nominal representation. In case of nominal representation, only names are written, like name of land cover classes. Ordinal means the names are written in order, or order is assigned, like first, second, third order, low elevation region, high, medium elevation zones, the higher elevation regions, that kind of order. And quantitative uh, representation means ratio or interval representation of the data. Ratio means interval means in this ratio and interval both, the attribute is represented in the form of numbers. But the difference in case of ratio and interval is, in case of interval, the difference of the uh, data is important, and ratio of that becomes meaningless. For example, if you want to represent year, year is also represented numerically, year 2020, 2010, 2012. Here difference of the year is meaningful quantity, like 2012 minus 2010. So you will get 2 years of difference. But when you find out ratio 2010 by 2012, it becomes meaningless. It's nothing. You cannot explain that ratio. So which means year is a interval quantity. So which means for interval kind of data, addition and subtraction can be performed, not ratio and division. But in case of ratio scale of measurement, uh, all the four operations can be done: addition, subtraction, division, and multiplication. So we moved away from our topic of uncertainty. For example, land cover class, that is forest or cropland, water body, their categorical value, while population, temperature are example of quantitative representation. Why I am telling this? Because the assessment of the accuracy is different in case of quantitative and in case of qualitative. So if accuracy assessment of qualitative data need to be done, which means where names are given, in that case, a change analysis is, sorry, confusion matrix is created between the created attribute and truth. And based on the confusion matrix, accuracy assessment is done. But in case of quantitative scale of measurement of quantitative attributes, where numbers are given, like temperature value, elevation value, population value. So in that case, root mean square error, that is one of the measure of uncertainty in, or measure of error for quantitative data. So there can be root mean square error, mean squared error, mean absolute error. There are many metrics. Now, why the attribute uncertainty comes? What is the reason behind attribute uncertainty? One reason is our capability, our computer's capability to identify a feature. If we are not able to identify a feature properly, which means there will be error. Because if we are not able to identify properly, and we are assigning some attribute value, either class or anything, that may have error. We may assign correctly, but that may have error. And our ability to identify a feature properly depends on the resolution of the data, spatial resolution of the data. If we are identifying visually, along with spatial resolution, uh, for automatic way or for add-on information, spectral resolution or spectral bands also matters. If you are having a bigger spectrum of observation, you can do classification, identification even more properly by looking at the spectrum. But first hand, if we are looking at the FCC of any imagery, and if resolution of the imagery is poor, we cannot form the feature properly. And if you are not able to form the feature, which means some uncertainty error will be there. Another limitation, another problem which affects our ability to identify features properly, that is mixed pixel. I will try to tell what is mixed pixel. Suppose on the ground it is like this, it is cropland, it is forest. So whatever pixels are coming in this region where forest, completely forest is there, so these pixels, they are pure pixels. So pure pixel means the is signature is coming from signature is from the single class, single object, or reflectance is coming from the single object. So that is pure pixel. But in case of mixed pixel, assume a pixel is here where part of the pixel lies in cropland and part of the pixel lies in forest. So from this pixel, a different kind of reflectance will be measured, which will not be exactly matching with forest, and that will not be exactly matching with cropland. Because from this region, signatures from both were coming, and aggregated value is stored in CCD, in sensor. So now, how will you assign this pixel? Either you assign cropland to this pixel or forest to this pixel. If you are assigning this pixel in cropland, so what you will get? You will get digitization boundary like this, where this extra portion of forest will be assigned a cropland value. If you are assigning this pixel to forest, this extra portion, if you are assigning this pixel to forest, if you assign this pixel to forest, then this extra portion of cropland will go to forest. Yes, one pixel represents one value, but if it is for pure pixel, the value will be completely different. But if it is from the boundary of 2 pixel, the value will be different. And if value is different, its appearance will be different. And because of different appearance, we will not able to identify which side it lies. So here we can see uh, if it is assigned in the cropland, this extra portion of forest will be assigned cropland value. So for this reason, there will be attribute error. And also, if you look at the boundary of the cropland, which was earlier this, but because of this mixed pixel issue, the boundary follows this pattern, this. So this way, Boundary is also having a error, which is uncertainty in the position of the boundary, uncertainty in the position of the cropland feature, and uh, error in the attribute assignment. This region is assigned wrong attribute. Our ability to identify a feature properly, if we talk about visual uh, feature identification, it depends on how a feature looks, how it appears, as well as how it is different from its neighbor, or how its appearance different from its neighbor. How do you identify cropland and a forest? If you look in true color composite, both of them appears green. If you look in false color composite, NIRR and uh, blue, uh, NIRR and green. So if uh, you are looking in false color composite, you will see that forest and cropland, they are appearing in the shade of red, where cropland will appear pinkish and forest appears reddish. So here we are able to identify, or we are able to discriminate between forest and cropland because of difference in the contrast, difference in the colors. So how different object appears from its neighbors, based on that feature identification is done. And if contrast of the image is poor, which means you will not be identifying objects properly. Obviously, you will be able to identify the objects, you will be able to identify the features which are completely different. Like you will be able to separate between forest and water body. They look completely different. But when it comes to identification of uh, scrub and cropland, it becomes difficult if contrast is poor. So if we are not able to discriminate properly, then there may be an error in attribute as well as position. If there is error in position, there will be error in attribute also. So atmosphere plays a role to decrease our power of discrimination. How? From the atmosphere, some noise is added in the data, and because of that, contrast of the image gets affected. So if contrast gets affected, our ability to discriminate between feature gets affected. So because of atmospheric effect, attribute uncertainty can come while you are creating the data. Though there are models for atmospheric correction, flash model, they do corrections, but obviously uh, there may be some uh, error in the correction process also. Then uncertainty can be there because of aggregation and disaggregation or disaggregation of the data. Suppose you have suppose you have created the data at uh, very high resolution, and later on you are doing aggregation to increase the pixel size of the data. So because of this process also attribute uncertainty may come. Because what we do in aggregation, for example, here you are having cropland for this pixel, cropland for this pixel, cropland for this pixel, forest for this pixel. So suppose earlier data was created at 10 meters spatial resolution and now you are doing aggregation at 20 meter. So which means 10 plus 10, 20 and 10 plus 10, 20. So which means 4 neighboring pixels will be grouped to find to get one single value. What will happen in this case after aggregation? You will get a bigger pixel of 20 meters, but if these pixels are being combined, which value should be kept here? Cropland or forest? So since majority is cropland, so cropland will be put here. Anyway, there are different methods of aggregation. Nearest neighbor, average, finding out average, fitting a bilinear interpolation method. There are different methods for aggregation depending on the qualitative scale and quantitative scale. So finding out the majority is one of the methods for qualitative data where names are given. So whichever category is having larger number, that will be assigned here to this pixel. So now because of this aggregation process, this pixel, one pixel which was cropland previously, uh, this location was this location was defined as forest previously, but because of aggregation, that location is also marked cropland. So here, by doing this, what you can notice, earlier boundary of cropland was this, but now because of aggregation, boundary of cropland has become this, which means there is error in the boundary of cropland now, and since there is error in boundary of the cropland, there is error in the attribute value also. This area was supposed to be the forest, but it is cropland. So uncertainty in boundary as well as uncertainty in attribute is introduced because of aggregation process. These are the labels from which, because of which attribute uncertainty can be there. Then for doing accuracy assessment, and if you have to do accuracy assessment, you need a reference data set to do accuracy assessment. Accuracy assessment is like comparing your results with the reference data. And the reference data, whichever is being considered, you should have enough justification, or you should be convinced that the data is of high quality. You should have enough reasons to believe that data is of high quality. And how do you define high quality for reference data set? Based on the parameters of data quality, means the data set which is being considered as reference data set, that should have very good accuracy in the form of attribute as well as in the form of position, and those accuracy assessment must have been done data should be complete in nature, logically consistent. So those things, if your reference data set is qualifying, then you can use it as a reference data set. Otherwise, you may collect samples from ground using high accurate device. If you are doing that, then only accuracy assessment can be done. Position accuracy also comes because of our lack of ability to identify feature boundary or identify feature itself, and how our ability is affected because of randomness in nature. Natural boundaries are not very well defined. Then it comes because of lack of observation. In the previous lecture, we have discussed about GPS observation. We have discussed that any measurement is having some systematic bias which is constant throughout all the measurements, plus some random error component. Random error component because of anything, because of the handler person, because of environment condition, because of instrument, because of anything, random errors can be there. So it can be either positive or either negative. In some observation it will be positive, in some observation it will be negative. So if we increase the number of observations, the mean, and find out mean of all the observations, then the random error component becomes zero, or it tends to zero when number of observations becomes larger. But when we are keeping our observations very small in number, then our data set will have systematic bias as well as random errors also. Then practically immeasurable, sometimes it becomes practically immeasurable to find out the feature or find out the boundary because of uh, reasons which we have seen previously for attribute uncertainty, where if there is mixed pixel, difficult to find out the feature. If pixel size is larger, obviously we cannot identify very small objects on the ground. If there is shadow, uh, maybe because of trees, because of high-rise buildings. So if because of these shadows, the exact boundary you will not be able to identify. Because of the canopy cover, you cannot identify the exact boundary. So these are the practical limitations. So if these things are there, positional uncertainty will be there in your data. Error in the location of point object, error in the placement of line, error in the placement of any polygon. Now we will move towards error propagation, how error is propagated. Generally, as already told, when we are creating the data, our purpose is not just to create the data, our purpose is to get some information from the analysis of the data. So many times we fit a regression model, we do adjustment in digital photogrammetry, we try to build 3D model, we try to calculate area of the classes, aggregation, disaggregation of the data. We may look for the vegetation productivity. For that, we need to look for the NDVI, EVI values and correlate it with the productivity. So in each case, what is being done? We are having some input variables, can be in the form of raster data, that is image, or it can be in the form of vector data, that is point, line or polygon. These input variables go to your model and you will get some output depending on the model. So a model is made of equations with parameters relating input and output variable. So model is the mathematical equation relating your input and output variables, which is having some parameters also. So input variable, they are observed quantities you need to observe, and you pass those values variables and you will get output. But as you see, model have some parameters also. So those parameters need to be estimated. There may be a additive parameter, multiplicative parameter. Those parameters need to be estimated, and each parameter will have its own uncertainty. Because of uncertainty in a parameter estimation, your output will have some uncertainty. That is one way of uncertainty. Another is error in the concept of model itself. For example, you are trying to relate NDVI with the crop productivity. So you may have tried relating them with using linear model. So if you are relating them with linear model, so there may be possibility of uncertainty in the parameter estimation of the model, or there may be error in the concept of the linear model. What I mean, there may be the situation where linear model doesn't fit to that process. There may be there may be the best suited model for that agriculture productivity, polynomial model or some XYZ model, and we are fitting a linear model. So the model itself is not right. So because of that, results will not be right. So as a scientist, we should be uh, knowing about the process, and we should be knowing about the uncertainty in the modeling process. Until we know what kind of uncertainty can be there, we will not be doing justice to our results, because model is the equation, and if you are putting any XYZ equation and giving input, you will get some output. But is that output correct? Is that output interpretable? Those things we should keep in mind. A simple model equation is like this. Consider a simple model. This is a first order polynomial or a linear model. So here x1, x2, you can see these are the inputs, variables. The y is the observed, x1, x2, they are observed or independent variable. Y is the dependent variable, which is dependent on x1 and x2. So for relating the model, we'll come to that later. And these B0, beta 0, beta 1, beta 2, these are the parameters of the model. So now to find out the parameters, we need to relate x1 and y, x1, x2 and y first. So for some of the samples, we need to be knowing y, x1, x2 both, then only beta 0, beta 1, beta 2 can be calculated. For example, the relationship of crop productivity with NDVI and rainfall. So x1 can be NDVI, x2 can be rainfall, and the crop production in terms of weight in previous years. So this way, these parameters can be calculated. If we are having large number of observations for y, x1, x2, we can fit a regression here and find out beta 0, beta 1, beta 2, and the epsilon is the random error term. So as I told earlier, here what are the stages for uncertainty? Uncertainty can be in the estimation of parameters beta 0, beta 1, beta 2, because they are estimated statistically. There is a possibility of error. Error is possible in the conception of model itself. This linear model may not be suitable for the process it is used. So, and another stage of uncertainty is these input variables itself. So, if any one of them is having error or uncertainty, your output will have uncertainty or error. So, if either the model itself is having error, or either the model equation is wrong or it is error prone, or if parameters are wrongly estimated, or if observed or independent variables are measured wrongly, they are having errors, then collectively these errors will propagate to y. Here you can see x1 was measured independently, x2 was measured independently, beta 0, beta 2, beta 0, beta 1, beta 2, these constants are collectively calculated using x1, x2 and y, and later on we can see the beta 1 which is statistically estimated, x1 which is observed, and then if there is error in any of them, the collective error will be propagated to y. So that's why error propagation is additive in nature. So here you can see if x1, x2 are having errors, the estimation of beta 0 or estimation of parameters will have error, because initially from historic data, if we pick x1, x2 and y, if they are having errors, there will be error in parameters, and if there is error in parameters and error in input variables, collectively they will add up and more error in y will come. So in detail you can look that with alpha amount of error in x1 and gamma amount of error in x2, how much will be error in y. So there is a derivation for them. If you are interested in exploring more, you can explore with having alpha quantity of error in x1 and gamma quantity of error in x2, how much error will be in y. So ultimately one can say all models are wrong but some are useful. So which means researches are going on based on the identified evidence that which model is better. So we try to build better each year. Every researcher tries to build a better model day by day, and each model is having certain error in the form of conception, in the form of parameter estimation, in the form of numerical errors, whatever. But some are useful, means some models are approximately able to capture the natural process happening. For example, the linear or non-linear, if you try to fit the relationship between NDVI and crop productivity, you will see that generally it is a linear relationship with certain deviation, but deviation is very lesser, so that model is more or less useful. Straight away, it cannot be rejected. But yes, there are better models going on to capture non-linearity in the data. So if machine learning concept is used to find out crop productivity or predict crop productivity from the imagery, uh, that is a better model compared to linear. So for regression model, it is very easy to identify, it is very easy to estimate parameters standard error, and confidence interval, prediction interval of parameters can be estimated easily. But when it becomes a non-linear model, exponential model, logarithmic function comes into picture, it becomes very much complex, then identification of parameters is not uh, very easy. Sorry, estimation of parameters and their error estimation is not very easy. So in those cases, some approximation of model itself is done in the form of polynomial using Taylor series to so that we can easily find out the expected error propagation. So Taylor series is another way of doing error propagation analysis. And error can be because of this also. Most of the time, many geographic features need to be combined for geographic processing. So you may be combining line with polygon, and you may be doing overlay analysis, statistical analysis, many things you can do in GIS. So if any layer is having error, that will lead to error in your output. And obviously, when you do conversion from vector to raster, raster data to vector data, it is possible to convert. You input data to your tool, it will convert. But as you know, the raster representation is in the form of pixel, and if you convert it to vector, you will not get smooth line. You will get a zigzag pattern. For example, uh, you are having, for example, you are having a straight line like this, but the moment you convert the straight line to raster, you will get this type. So that is error in the position. Error due to rasterizing a vector map. When you rasterize any vector map, so these kind of errors you will get. Any point like object will be represented in the form of area, which means suppose a single point which was in the form of vector, and you are rasterizing it in the form of polygon. Sorry, you are rasterizing that to vector data at the a resolution of 10 meters, so the area of that point will become 100 square meters, 10 by 10, 100 square meters. So that is error in position of the point itself. Next pixel we have seen too much. This is end of my lecture today. You can post your queries